Lecture 27, we're gonna start on, continue on big assembly programming. We talked about multiple registers. If you have operations on multiple registers, you need to use the working register to transfer the value and use the working register to perform these operations together with the other register. We discussed conditional jump instructions, and we've seen many examples using conditional jump instructions, represented by this BTFSC and BTFSS plus goto. And we can use subtraction instructions to replace CMP, because we don't have really CMP instruction in PIC. And there are different condition code you may get when you do the subtraction, and you can then later use these condition codes to do the conditional branch. For shift and rotate, you will manipulate the carry bit before the operation, and for multiple bit shift or rotation, you need to use loop instructions or loops to implement multiple bit shift and rotation. Logic operations can be done byte by byte, and arithmetic and rotate shift instructions require you to count for data flow between bytes. The orders of these operations is important. For arithmetic instructions, you will do at least significant bit first. This is for the rotation and shifting. And then you're going to move through the bytes the same order as the shift. But for rotation instructions in PIC, both left and right, they will go through the carry bit. But for shift instructions, they will not. We're going to show here an example to work with data that's more than a byte. We know all the registers in the PIC, 16F or 18F, they are all 8-bit registers or a byte. If we want to work with a larger number, let's say over 256, or a 16-bit number, how do we do that? Using these individual byte-wide registers. In this example, we assume to have a 16-bit counter. Okay, the range of this counter could be from 0 to the power of 16, so that's a much larger number than the 256. We're going to store this counter in two registers, the upper half and lower half. Okay. The upper byte of the counter is called count H. You can think about we store the value into a variable or a register named count H. The lower byte is called count low, count L. Let's say we want to decrement that counter. When we do decrementation, well, forget our PIC, forget our x86. When you are given this 16-bit counter, you can do manually do the decrementation. You can subtract 1 from this number, right? So what are you going to do mathematically to implement this subtraction? You will write down a number on a piece of paper or on the board. You will put 1 at the least significant bit side, right? And you do byte or bit by bit subtraction. You may borrow a bit. But if you divide, think about this. If you divide the 16-bit number into two halves, the upper byte and lower half, when you decrement the number by 1, you actually decrement the lower half by 1. assuming you don't borrow. Let's say your lower byte is a 5. The upper byte is a 6. Okay, so you have 6 5 in hexadecimal. If you can't visualize the number, you can write it down on a piece of paper. So you have 6 5 hexadecimal value for the counter, and you subtract by 1. So what will be the result? 6 4, right? Because you have 5 on the lower half, and 5 subtract 1, that's 4. You don't touch the higher half, the upper half, which is good. So it's easy, and we're done. Now think about when you have 6 0 hexadecimal, and you subtract 1 from that number. Oh, that's too hard. So you have 6 0 hexadecimal, you subtract 1 from that number. Okay, think about what number when you add 1 becomes 6 0. So this is the original value in my counter, 6 0. I will need to subtract 1. So what is the number? 5 something, huh? It's 5F. So yes, it's a little bit more difficult than 6 5 minus 1, because you have to borrow a bit. What happens here is, when we do the subtraction, because we have a 0 here, so we need to borrow 1. And when we borrow, that becomes 1 0, and that's 16. Okay? So this hexadecimal. 16 minus 1, that's 15. So this F is the 15. And because you borrowed 1 bit, that's 5. But when you think about these two cases, the first case is 6 5. You got 6 4. And for the 6 0, you got 5F. But for both cases, we're actually doing the same thing. We are looking at lower byte. Well, this is not the byte. I think this is not a perfect example. This is the lower half, 4-bit, but it's essentially the same thing when we consider larger numbers. We will consider the lower half first. Chances are we don't need to borrow, then we can just subtract that number by 1. If we do need to borrow, we'll just borrow and then do the subtraction. So we're actually working on lower half and the higher half. Let's look at the 4 instructions we have here. First instruction is to move F, count L, comma F. This instruction is to copy the value of count L back to count L and update the flags and update the Z flag. So this first instruction will not change the value of count L. It will, however, update the 0 flag. So this is to really check whether the lower half is a 0 or not. Because you know, if the lower half is 0, we're going to do differently. Let's say this case is not a 0. Okay? it's not a 0, then this 0 flag will be a 0 to indicate it's not a 0. The second instruction, BTFSC. Bit test a register, skip if that bit is clear. So in this case, the 0 flag is a 0. Indicate this 5 is not a 0, right? So when we execute BTFSC, do we skip or not skip? We skip if 0 bit is cleared. So we will skip. What instruction do we skip? We skip decrement high. So we'll not decrement this digit. We just execute the last one, which is decrement the low.
So decrement high, we will skip decrement high?
Yes, for this case. We will skip decrement high. So that's how we really get this 64, because we skip decrementing the high byte, and then we decrement the low digit.
Because it doesn't specify which one is going to skip.
It'll skip the very next instruction.
Oh, okay.
Yeah, it's always that.
Yeah.
Now for this case, when we do move F, I want to change a little bit here to make it right. Because we're talking about a byte. Okay. This is control I. We're talking about byte here. So when we do move F, count low F, what will be put into the 0 flag? We have count low 0. So when we copy the value to itself, the ALU will update the 0 flag. So the 0 flag will be 1, because it is 0. Next instruction, BTFSC, status Z. So when we check the 0 flag, we will skip the next instruction if 0 flag is clear. It's not clear, right? So shall we skip? We'll not skip. So we're going to do decrement count high F. So what's going to happen is this upper byte will be decremented. So that's why you have 5 here. And then the last instruction is decrement count low. So the 0, 0 subtract 1, that becomes FF. This is the correct result, right? 5FF. That's exactly what the counter should be. So with these 4 instructions, you can effectively decrement or maintain a 16-bit counter and decrement it correctly. The next few instructions is to test whether a 16-bit variable is 0 or not. Let's go through these instructions. First instruction is similar as we did before. Move F, count L, comma F. This is really doing the testing to see whether this count L is 0 or not. If we have a 0, like in this case, if we have a 0, the 0 flag will be a 1. BTFSC status Z. When we have 0 flag is a 1, will this instruction then skip the next instruction or not? It will not, because the condition is not true. So it will not skip the next instruction. So what does it do? This is the next instruction. It will do the checking on the higher half, just like we did for the lower half. We're going to check whether the higher half is 0 or not. Let's say, yeah, how about we indeed have a 0 on the higher half. Then this second move F instruction will again have 1 on the 0 flag. And next instruction is do the checking again. So will we skip the next instruction? Because this is a 1, 0 flag is a 1. So when we do this BTFSC, will we skip the next instruction? We will not skip the next instruction because the condition, this condition C is not true. So it will do this go to both 0. So this is how we test whether the variable, the 16-bit variable, is 0 or not. If it is not 0, if either one of these bytes is not a 0, this instruction will not be executed. Only when both of them are zeros, this instruction will be executed. Now we have a few more examples. I'll just go straight into the solutions. First example is move ZX, AX, comma, BL. This is to do the 0 extension. Right? Remember? Move ZX, BL. This is to do 0 extension. So essentially we're gonna copy the value of BL into lower half of AX, and the upper half are all going to be zeros. That's the 0 extension. So we'll do copy the value of BL to W, because we cannot operate on the 2 registers directly. And the second instruction is to copy the value from the working register to AL, which is the lower half of AX, and then we clear the upper half. That's the 0 extension. The sign extension is to put the value to the lower half of the destination, and then fill the upper half with the sign bits. Let's see what we do here. We copy the value of BL to W, and then we copy the value from W to AL, which is the lower half of AX. We need to decide whether the higher half, the AH, is going to be all zeros or all ones. Right? And that depends on the most significant bit of a BL or AL. So we're going to first clear AH to just assume that we may have all zeros. If not, we're going to make it all ones. BTFSC AL, comma 7. What do we do here? We do bit test. We test the sign bit of BL. Remember, now BL and AL is the same. We test the sign bit of BL. If that bit is clear, we're going to skip this instruction. Right? That's BTFSC. We're going to skip this decrement instruction if my sign bit is a 0. If that's the case, because we already have AH 0, so we have the sign extended. So all zeros on the higher half. If, however, the sign bit is a 1, then this bit test skip, if it is clear, this condition is not true. So we'll not skip the next instruction. So we will execute this decrement F, AH, comma, F. This will decrement 1. We'll do H minus 1. You have 0 minus 1, and the result is going to be put back to AH. Again, just a reminder, by now you should already know that this F is not the hexadecimal number F. This is the indicator to say where is the destination. So AH will have FF, and that's exactly what we want to do for the sign extension. Let's stop here. I think we already have a lot of materials covered, and these examples, I would recommend you to go through the ones that I talked about in class. Make sure you really understand the translation between the Intel assembly language instructions to PIC instructions. In reality, you may not do this type of work exactly, do this translation, but the idea here is to understand, to implement a operation, a algorithm, what are the instructions you need for either x86 or the PIC. So let's continue on PIC programming. Here's what we were about to do last time. We're going to look at a delay subroutine. So a delay subroutine is a subroutine that will provide you delay. What we're talking about here is a subroutine in PIC assembly language that when you call the subroutine, it will give you a certain amount of delay. So the microcontroller will just do something, and after this subroutine is completed, it takes exactly that amount of time. This is very useful if you want to do some kind of timing related control. Let's say you want to switch the light from yellow to red in, say, 5 seconds. Then you can use this kind of subroutine to do that. Because in your main program, when you call the subroutine, you can set parameters so that the subroutine will take 5 seconds. Once the subroutine is completed, then you can do the light change. Okay, this is the idea of the delay subroutine. Well, keep in mind that there are other ways to do delays. You can use timers to do that too. This delay subroutine is one of the approaches. This subroutine is called the 10 millisecond subroutine. Now, we give it name 10 millisecond is because it really provides you 10 millisecond delay. And we'll look at how we exactly get that delay. This subroutine, it's called insert a delay of exactly 10 milliseconds into the execution of code. The assumption is that the microcontroller runs at 4 MHz crystal clock. As a result, one instruction cycle is about 4 of that cycle time. And this is a main assumption. This 4 MHz clock time is the main assumption here, because this clock time or this clock frequency determines what kind of initial values we need to put into the counter. We have a counter called 10 millisecond, and we break it into 2 halves, like we did for the 16-bit counter. So we have a 10 millisecond high EQU that equal 13. So this is to really define that symbol 10 MSH. That's the same as the value 13. And the next one, 10 MSL EQU 250, that's really define a symbol. This 10 MSH has the value 250. So in later programs, you can use this 10 MSH and 10 MSL to replace these 2 numbers. Everything here, starting with the semicolon, those are comments in the PIC assembly language program. And the reason we want to use 10 MSH and 10 MSL is that in your program, there might be many places that use these numbers. If you want to change the initial values for, let's say, for a different delay time, not 10 milliseconds, you may want to do 20 milliseconds. What you need to do is just change these values at the beginning. And then all the subsequent appearance of these symbols will have the new value. 10 MS, this is the name of the subroutine. And in the first instruction, we have NOP. NOP is no op, is instruction that does nothing. For our purpose, this is really an instruction that's going to consume 1 cycle. And then we have 4 move instructions. This is to initialize this count H and count L. Those are the registers we use to track the 16-bit counter. Remember we talked about the 16-bit counter example last class. And count H stores the higher byte of the counter, and count L stores the lower byte of the counter. Then we have this 10_1. This is a label, and we have an instruction here: decrement FSZ, count L, F, go to 10_1. This is what we saw in the 16-bit counter example. This is exactly the same. These 4 instructions here are doing the counting. It's decrement the counter, and we're going to decrement until it reaches 0. Okay, these 2 DECFSZ is to decrement the lower half, and then if the lower half is 0, we're going to decrement the higher half as well. That's what we did to decrement the 16-bit counter. And On the right, this is really the flowchart. I should have explained flowchart earlier, but we did see the same example when we discussed the 16-bit counter. So what we're doing here is at the beginning, we're going to initialize these counters, okay, count H and count L, the higher byte and lower byte. And then we do the decrement, and we'll check if count L is 0. If not, then we're going to just finish that, because we just need to decrement the lower byte. If the lower byte is 0, then we'll need to decrement the higher byte as well. In either case, we're going to check whether we have count high is 0. In that case, the loop will end, because the end condition of that loop iteration is when the count H is 0. That means we decrement all the way down to get to the 0. Now, you may wonder, how come we have this 10 millisecond using this 10 also instructions? It turns out that if you count the number of times these instructions are executed, they take exactly 100,000 instructions. And each instruction takes about 1 microsecond. So we're talking about overall 10 milliseconds. And the number of times these instructions, particularly these go to and these DCFSZ, these instructions will be executed. The number of times these instructions will be executed is determined by the initial value of these H and L, 10 ms H and 10 ms L. Because this initial value will be decremented by 1 at a time, and eventually this count high and count low will reach to 0. So with this initial value, we'll get these instructions executed exactly that number of times, and because we are running on the 4 megahertz clock, and that gives you exactly 10 millisecond time. So it's a little bit tricky to really determine the initial value of these counters to give you exactly 10 milliseconds. For some other cases, there might be a little bit error, maybe just 0.1% of error, depending on the initial value you set it to the counters, and also depending on exactly how these go-to instructions will be executed. Okay, now we will move into a more realistic example. Let's say we have this problem to solve using a PIC microcontroller. We want to blink LEDs and assume that we have 3 LEDs, green, yellow, and red. So these are the traffic lights. And these LEDs, those tiny LED components, are attached to the PIC, and specifically green is attached to bit 0 of port D, yellow is attached to bit 1 of port D, and red is attached to bit 2 of port D. We want to write a program for the PIC 16F874 that toggles the 3 LEDs every half second in sequence. What kind of sequence? It's green, yellow, red, and green, yellow, red. So it's like traffic light. Obviously, you want the traffic light to be more than half second, otherwise nobody's gonna cross the intersection. But let's assume that we want to do that, half second. Half second, that's 500 milliseconds. Right? And we just had a subroutine in the previous slide, which gives us 10 milliseconds. So in order to get 500 milliseconds, if we use this 10 millisecond delay subroutine, how many times do we want to call this subroutine? It'll be 50 times, right? It's 500 milliseconds, that's the total delay we want to get between the toggles. And each call to the subroutine gives us 10 milliseconds, so that's 50 times. Okay, so for this example, we'll assume that the system clock is also 4 megahertz. So how do we solve this problem? We start with high-level thinking. We want to have a top-level flowchart, which will guide us to the design of this program. We will need to initialize port D and initialize the counter for getting this 500 millisecond. Now, here we have two parts. Initialize port D. What do we mean by that? So port D is the I/O we use to control these LEDs. And let's say this for any single LED, one connection is to the port, to the pin of the PIC microcontroller. The other end of the LED is grounded. So what do you have to do to turn this LED on? You want to output a high voltage, right? So like 5 volts on this end, across the LED, and this is the ground. And that's how you turn this LED on. Or of course, depending on how you connect the polarity of the LED, but normally you would output high to turn on this LED. And to output a high, what we want to do is actually we're going to tell the microcontroller that we're going to use port D as an output port. For each pin of the microcontroller, you can use it as an input port or an output port. You choose either way. But you have to choose that. You have to tell the microcontroller that we're going to use port D as an output port. Also, maybe at the very beginning you want all the 3 LEDs to be off. That means not only you need to tell the microcontroller the port D is an output, you also want to output low voltage or logic 0 to the pins so that these LEDs are all off. Make sense? Make sense? Yes or no? Yes? Okay. So that's what we mean by initialize port D. The second phase is to do the blink. For blink, we want to toggle the LEDs in sequence. If it is green now, then next time we want it to be yellow. If it is yellow now, then next time we want it to be red. If it is red now, then next time we want it to be green. So that's the toggle. For doing this blink, for doing this toggle, we really need to know what is my LED, well, which LED is on right now. Because that will determine which LED to turn on next time. And in fact, which LED to turn off next time. Because when you do toggle, if it is green now, you need to turn off green, turn on yellow, right? That's 2 operations. That's how you do the toggle. So after you toggle that LED, so you switch from green to yellow, then you need to wait that 500 millisecond or half second. That's where you will call the 10 millisecond subroutine for 50 times. And once that's done, you will come back to do the blink again. So on the right, you see this is what we just explained. You need to initialize everything, everything that you need. Then you need to do the blink. Then you wait for half second, come back to the next blink. So how do we do the blink? We know we want to toggle these LEDs in sequence. So let's use this flowchart on the right to explain the procedure. We will read current port D state. Because we use port D to control these LEDs. Inside the PIC microcontroller, we can read the value that's currently outputting on port D. From this value, we can tell which LED is on, which LED is off. Okay, so let's say if we connect the LEDs in such an order, this bit 0 is an indicator what is connected to green, and this middle one is to yellow, and this leftmost one is connected to red. So we can just check that 3 bits from port D, the register, and we'll see, do I have a 1 here on the least significant bit? If I have a 1, that means right now the green LED is on. So what we need to do is we need to change it to yellow. How do we change it to yellow? We'll just change the value from 001 to 010. So there are 2 bits changed. This green is changed from 1 to 0, and this yellow is changed from 0 to 1. So that is turn off the green, turn on the yellow. Now for the other case, if we do not see green is turned on at this point, then we'll check whether we have a yellow LED is on currently. If that's the case, then we need to change it to red. And the way we do that is to change this 3-bit value from 010 to 100. So as we mentioned earlier, this leftmost bit is connected to red, and we want to make it 1 so that we'll output a logic high, like 5 volts, so that will turn on the red LED. Now, if currently it's not green or yellow, then there must be red or something else. In that case, we'll just turn on the green LED. So the overall principle we have here is that the next LED to be toggled is determined by the current LED. So by changing the values on these 3 bits out of port D, we can toggle the 3 LEDs. So once we decide this strategy, we will write down PIC assembly language instructions to implement this procedure. So this is the subroutine we could have. Blink is the entry point or the name of the subroutine. The first instruction is BTFSC port D, 0. Now, this is the instruction we talked about in the previous classes. This instruction will do bit test a register, and in fact, we're going to test bit 0 of register port D. We're going to skip the next instruction if that bit is a 0. Okay? This SC here is to skip if the next instruction is if the bit is a 0. If bit is a 0, we're going to skip the next instruction. In other words, if that bit is not a 0, that means that's a green LED. So currently, we have green LED on. And if that's the case, we will not skip the next instruction. That means we will execute this, go to toggle 1. So what do we do at toggle 1? Toggle 1 is to clear bit 0, set bit 1 of port D. Again, these 0 and 1, these are the index of the bits in port D register. So in toggle 1, we change the LED from green to yellow by changing the value from 001 to 010. And then we return. So that case is done. Now suppose when we check this bit 0, it's indeed a 0. That means the green LED is not on at this point. Then this go to instruction will be skipped. So we're going to check this port D, comma 1. We're going to do the bit test, skip if it's clear. That is to check whether currently we have yellow LED is on or not. And if that's the case, we will go to toggle 2, which will essentially change from yellow to red, and then we return. In toggle 0, that's the case. When we have a red LED on, then we're going to change it to green. Okay? So this program here is an implementation of the flowchart we have on the previous slide. Do you have any questions? Now here is another way to code the blink. We can use tables. What we have here is really a table that stores the values we will. Let's put it this way. Blink table is a subroutine. Okay? Blink table is a subroutine, just similar as the blink. This is the entry point of the subroutine. And as you can see, it has a lot of different return LW instructions. Return LW instruction will return from subroutine. Also, before it returns, it will put this value to the working register, then return. Okay, so this RETLW actually does two things. Put this value into the working register, then return from the subroutine. Now, when we get into the subroutine, first thing we want to do is we're going to copy the value from port D to W, and then we're going to do a mask to just look at the least significant 3 bits. I hope you are following me at this time. So the first instruction is to copy the value from port D to the working register. Second instruction is to AND operation on 2 numbers. One is number in the working register. The other one is this 111 binary. Everything AND with 0 becomes 0. Everything AND with 1 becomes stays the same. So let's say if I have 001 port D. This is the least significant 3 bits of port D. So this is my green, this is yellow, this is red. So what do we have here? Green LED is on. When we do this move F port B W, so W will have this 001. Okay. Second is N LW this B 0000111. So this value will be ANDed with this value. So what will W have? Okay. So this is really trying to ignore whatever upper bits we have. And this instruction makes sure that W will be a number from 0 to 7. Right? Because we mask out all the alphabets. So the second instruction, we have a value in W, which is in the range from 0 to 7. Next instruction is to add WF PCL F. Now, you may not remember this PCL, but this PCL is the lower half of the PC, program counter. We have PCL and PCL-APH. This is the value pointing to the instruction the microcontroller is trying to execute next. And what do we have here? Okay, RETLW. Secondly is RETLW. Okay, then we have some more. Okay. And we have in the main program, we have table or okay, so well, the reason we can get to here to execute these two instructions is because of this call, right? We call this building table process execute these instructions, and then we have here, in our case, 001 is W. Now we're about to execute this instruction. We are about to execute this instruction. When we execute this instruction, this PC is actually pointing to here because this is the next one to be executed. Okay, this is a little bit tricky to understand. When the microcontroller is executing this instruction, this add WF, the value in PC is pointing to this location. Okay? The address, the value of the PC is the address of this instruction. This is an addition operation. It's going to add W onto this PCL. Right? Add WF is add two numbers. One is W, the other one is this PCL. Comma F, that is to say, the result goes into that register. So that's PCL. So what do we add to PCL? We're adding 1 to PCL. Right? Because at the beginning we know we have 1 in W, so W still have a 1, and this addition will add 1 to PCL. So that is to say, hey, I'm going to execute this instruction. This is adding 1, okay? What is in PCL? What exact value? We don't know. But what we do know is it was pointing to this instruction. And because we added one, so now it's pointing to this instruction. And this is the instruction the microcontroller needs to execute after this addition is completed. It's like you did a jump, but you control the distance of the jump by using the value in W. Okay? You follow me? Okay, now we get to here, this instruction. What do we do in this instruction? This instruction is RETLW. So when the microcontroller executes this instruction, it will put this 011, of course upper 50, into working register, and then return. Okay? Wait, that's just two things. Yeah. So when the microcontroller tries to execute this ADD instruction, the PC is already pointing to the next one. Yeah, it's always pointing to the next one. It's always going to point to the next one, next one. Because the microcontroller needs to know which one is the next one. It already knows, oh, I'm going to execute this one, but what is the next one? This instruction itself will change that pointer because we're adding a value, which is 1, onto this PCL. This is the PCL, part of the PC. So it will change this pointer to here. You don't need. The microcontroller just needs to know, oh, that's the next one. This is no longer the next one. This is the next one. Once we get to here, we're doing two things. Put 001 into W, and then return. When we return to here, right? Because that was after the call. We return to here. Remember we have this is what we put into W right before we return. So we have this. And this instruction is to do exclusive OR. So whatever value in port D, in fact, what is in port D? This was in port D. And when you do XOR on these two numbers, so we'll now have 1, 0. And because this F flag, this result is going to go into port D. Remember F or W? The second operand is the flag. If it's F, that means the result is going to go into this register. If it's W, the result is going to go into the W register. questions? Yeah.
So I just want to go to the return of W function. Let's call the table.
Now, the reason we call it like a table is because we have a bunch of return LW instructions. And we can get to one of them, but that depends on the exact value in W. Okay. Well, you don't have to have return LW. You can have any instruction, indeed. But with this return LW, you can get a value into W before you return. And that value, if you pay attention, this number and other numbers, for example, the next one is 110. You often see two ones, and these two ones are the places you want to do the inversion. With these two ones, you actually inverted this green light and yellow light. Green light and yellow light. Because they're doing exclusive OR. Everything you exclusive OR with one, you invert it. So what we're really doing here is, hey, if you have a green light, then take the lower 2 bits, invert them. That's how we got this yellow light. Let's say if you have a yellow light, So that's 1, 0, that's 2. So you get to this one. Right? Because you're adding 2. So you're adding 2, that's going to be here. So this will be in the working register when it comes to here. This is going to be 1, 1, 0. So you're going to invert these 2 bits. So you will have a red light. Because that's the 2 bits you invert. Yeah.
Whatever is in the working register, that's going to tell you where to skip to, what you're trying to skip to.
Yes,
Because you're going to add that to the PC.
Exactly. It's just instructions, okay? Don't make it too complicated. The microcontroller just executes instruction by instruction. When we get to this add WF, that's an addition. The only difference, or the tricky thing here is, what adding the W comes to this PCL. PCL is a special register. It's the pointer. It's the register that tells the microcontroller where is the next instruction. And that's why, depending on the value of W, we will get to different instructions in this table. And which is smart enough to put that 2 ones to proper invert. Any other questions? Good.